Hello students, good day. I hope all of you are well. In the previous session, we discussed the first CPU scheduling algorithm, that is first come first serve, that comes under the category of non-primitive CPU scheduling algorithm. Today we will discuss two more algorithms of the very same class, shortest job first and priority scheduling. all three all these three algorithms, they fall under the category of non-primitive CPU scheduling algorithms because in this class, once a process enters the processor, it would not come out unless it completes its execution. And in the coming sessions, we will discuss about primitive algorithms, which are of the nature where we can take them out before they have completed their execution. So in non-primitive class, once a process is scheduled for the processor, it will remain in there unless it completes its execution. So shortest job first is the second algorithm of this class. In this algorithm, we select a process having the least requirement for the burst time. At any given instance, out of all the processes that are present in the ready queue, we select a process that is the shortest. So for instance, if we have multiple processes having time requirements of 1, 2, and 3 seconds, we will pick up the process that has the burst time requirement of 1 second. So in this way, we always pick the shortest process that is available in the ready queue. For this algorithm, a tag is associated with each process that contains the burst time requirement of that particular process. The scheduler, it uses those tags to select a process having the least burst time requirement and pass it on to the processor. So in this way, from a pool of multiple processes waiting in the ready queue, the process having the least burst time requirement or having the shortest requirement for the processor will be picked up by the scheduler and passed it on to the processor. In this way, because every process has to wait for a process that is shorter in length with this process, so shortest job first provides the minimum average waiting time because there is no convoy effect. No process has to wait for other processes that are longer than itself. So in this way, shortest job first is optimal and provides the minimum average waiting time among the rest of the uh, algorithms. However, there is a downside. It is also a possibility that a process that has a longer burst time requirement, it may uh, wait for a longer time if there is a constant supply of multiple short processes. And definitely, if a process that has a longer requirement and if it's waiting and small processes are coming at a constant rate, then this process may have to wait for so long that the execution of this particular process or the operation that it has to perform, it may become irrelevant. We in operating system, we call or we term this concept as starvation, where a process has to wait for so long that the execution of this particular process becomes irrelevant. We call it starvation. So a process may wait in the ready queue for so long that there is the operation that it has to perform, or the task that is required by the execution of this process, it becomes irrelevant. We call it starvation. So in shortest job first, if a longer process is waiting in the ready queue and there is a constant supply of short processes, it is very much possible that this long process may starve. So starvation is one disadvantage of shortest job first. So over here we have an example of shortest job first. In this example, we have four processes from P1 to P4, and their burst time requirements are: for P1 it is 6 seconds, for P2 it is 8 seconds, for P3 it is 7 seconds, and for P4 it is 3 seconds. So these are the burst time requirements for all these four processes for shortest job first. Now, if all of these processes they arrive in the ready queue at time interval 0, then the scheduler has to pick one of them and pass it on to the processor. So as you can see that over here we have P4 having the least requirement for the burst time, so it should be picked up first by the scheduler, followed by P1, P3 and P2. So you can see that shortest job first takes processes based on their burst time requirements. So the Gantt chart for this scheduling algorithm would be that first of all P4 will be scheduled for the processor by the shortest job first scheduling algorithm at time interval 0, while all the other three processes P1, P2 and P3 they will be waiting in the ready queue. So once P4 completes its execution, as this is a non-primitive algorithm, it will only come out once it completes its execution. So once P4 completes its execution, then out of these three processes P1, P2 and P3, we know that P1 has the least requirement for the burst time. At time interval 3, P1 will enter into the processor and it will complete its execution at time interval 9. In the meanwhile, P2 and P3, both of them will be waiting in the ready queue. At time interval 9, the ready queue has two processes P2 and P3. This time, as you can see that P3 has the least requirement for the burst time, so P3 will go into the processor while P2 will wait in the ready queue. After P3 completes its execution at time interval 16, the only process that is present in the ready queue is P2. Then P2 will go into the processor, and once it completes its execution, it will come out at time interval 24. So now you can see that shortest job first selects processes based on their burst time requirements. Now, as we had seen in the first come first served algorithm, it is recommended that you may calculate the average waiting time for each of the process on your own. So you can just stop the video over here and you can calculate the average waiting time for each of these processes. And once you have calculated it, you can continue the lecture just to confirm your results. So over here, as you can see that for P1, it arrived at the system at time interval 0 and it went into the processor at time interval 3. So 3 minus 0 will be 3, as the waiting time for process 1. For process 2, it arrived at the system at time interval 0 and it went into the processor at time interval 16. So 16 minus 0 will be 16 as the waiting time for P2. Then for P3, it arrived at the system at time interval 0 and went into the processor at time interval 9. So 9 minus 0 will be 9. And for P4, it arrived at the system at time interval 0 and went into the processor at time interval 0. So 0 minus 0 will be 0. So once you add all of them, you will get 28 and you divide it by the number of processes, that is 4. So you will get the average waiting time for this algorithm for this particular scenario, that is 7. So 7 will be the average waiting time for this particular example. So now you can see that we in the previous session we had an example and we calculated the average waiting time for first come first served, and in this example now you are able to find the average waiting time for shortest job first. Now, for any given scenario, you should be able to calculate the average waiting time for first come first served algorithm as well as shortest job first algorithm and determine which of them performs better under what circumstances. Alright, so over here students, we have a class exercise for shortest job first. In this exercise, we have 4 processes P1, P2, P3 and P4 having the burst time requirements of 7, 8, 4 and 3 seconds respectively. If all of these 4 processes arrived at the ready queue at time interval 0, you should be able to calculate the average waiting time for this particular scenario. So first of all, you should draw a Gantt chart for the whole scenario. Then you may find the waiting time for each of these processes and then calculate the average waiting time for the whole scenario. So now you can stop your lecture over here for a while and do this exercise and continue once you have done this complete exercise. Over here we have the Gantt chart for this exercise. So as you can see that in this particular scenario we have P4 having the least burst time requirements, so it will go in the processor first. As it is a non-primitive type of algorithm, it will only come out once it has completed its execution. So at time interval 3, we have 3 processes in the ready queue, and among them P3 having a burst time requirements of 4 seconds is the shortest process. So P3 will go in the processor, followed by P1 and then P2. So you can see that this will be the Gantt chart for this particular exercise. Now once this Gantt chart is developed, now we can easily calculate the waiting time for each of these processes and then the average waiting time for the whole scenario. So over here as you can see that for P1 it went into the processor at time interval 7 and as all of these processes arrived at time interval 0, so we can straight away take 7 minus 0 as 7. For P2 14 minus 0 is 14. For P3 3 minus 0 is 3, and for P4 0 minus 0 is 0. So if we just add them together and take their average, so we will get 6 as the average waiting time for this particular exercise. Now let's add another concept on top of it. What will happen if multiple processes are arriving in the system at different times? So how can we compute the waiting time of multiple processes if they are arriving at different time intervals? And how can we compare its waiting time with others? To calculate this, let's have a scenario. So over here we have four processes, P1, P2, P3 and P4, having their burst time requirements of 6 seconds, 8 seconds, 7 seconds and 3 seconds respectively. Now they are arriving in the system at different time intervals. So for P1, assume that it arrives at the system at time interval 0, P2 arrives at the system at time interval 2, P3 arrives at the system in time interval 4, and P4 arrives at the system at time interval 7. So now you can see that they are arriving in the system at different time intervals. So at any particular point, there will be different processes and their presence will be entirely different as compared to the previous exercise. So how can we develop the Gantt chart and how can we calculate the average waiting time for this particular scenario? So let's try this. As you can see that at time interval 0, there is only one process present in the system, that is P1. P2, P3 and P4, they have not arrived in the system yet. So no matter which algorithm you use, as this is the only process present, it will be picked up by the scheduler and passed on to the processor. So this time P1 will be given to the processor for its execution. And as this is a non-primitive algorithm, we will only look at the situation once it completes its execution. So we will again look at the ready queue at time interval 6 once P1 completes its execution. So at time interval 6, we have two more processes waiting in the ready queue, that is P2 and P3. And now as there are two processes, now we will look at their burst times. So as P3 has less burst time requirement compared to P2, so P3 will be picked up by the scheduler and passed on to the processor. Once P3 completes its execution, then at time interval 13 we will again have two processes in the ready queue, process number 2 and process number 4. Now we will check their burst times, and as P4 has less burst time compared to P2, P4 will be given to the processor. And then at the end, P2 will be given to the processor for its execution. Now let's have a look at how can we develop the Gantt chart for this example. So here we have the Gantt chart for this exercise. So as you can see that at time interval 0, we have only one process and it has to go in the processor no matter which algorithm we select. After it comes out at time interval 6, now we have two other processes, P2 and P3. As P3 is shorter compared to P2, it will be given to the processor by the scheduling algorithm. Now at time interval 13, once P3 completes its execution, now we have two more processes in the ready queue, that is P2 and P4. As P4 is shorter compared to P2, so it will be given to the processor. Once it will come out at time interval 16, now we have only one process remaining in the ready queue, so it will be given to the processor, and at time interval 22 it should complete its execution. Now in this scenario, through this Gantt chart, now you should be able to calculate the waiting time for different processes. However, this time you have to take into consideration the times at which they have arrived. So for P1, as it has arrived at time interval 0, that should be straightforward and comparable to the exercises that we have done so far. For P2, as you can see that it was given to the processor at time interval 16. However, it arrived in the system at time interval 2. So it waited for 16 minus 2 times, or 16 minus 2 seconds. So you can see that this time, to calculate the waiting time, you have to consider the arrival time as well. So let's have it. Let's calculate the average waiting time for all the processes. So here, as you can see that P1 arrived at the system at time interval 0 and went into the processor at the same time, so it has to wait for 0 seconds. For P2, it arrived at the system at time interval 2 and went into the processor at time interval 16, so it has to wait 16 minus 2 seconds, that is 14. For P3, it arrived at the system at time interval 4 and went into the processor at time interval 6. So 6 minus 4 will yield 2. For P4, it arrived at the system at time interval 7 and went into the processor at time interval 13. So it will yield 6 as the waiting time. So if we take the average of all of the waiting times of these processes, we will get 5.5 seconds for the whole scenario. So you can see that how we can calculate average waiting time and waiting time for each of the processes under the condition when they are arriving at the system at different times. Alright, so the next CPU scheduling algorithm is the priority scheduling. In this algorithm, we select a process out of multiple processes present in the ready queue based on a priority associated with it. So for the implementation of this algorithm, we have to associate a tag with every process that reflects the priority of that particular process. There are various characteristics or properties that are associated with processes when they are waiting in the ready queue. One of these features or properties include the priority of a process. So priority scheduling algorithm utilizes this particular priority of a process to select a particular process among all the other processes that are waiting in the ready queue. So in priority scheduling, the scheduler selects a process having the highest priority among all the other processes that are present in the system and pass it on to the CPU for its execution. Usually smaller integers reflect higher priorities. So a process having a priority of 1 would be considered as having the highest priority among the rest of the processes. This priority scheduling has two versions. The first one is primitive and the other one is non-primitive. We will discuss the primitive one in its proper section when we will discuss other primitive algorithms. Over here we will only discuss the non-primitive version of priority scheduling. If you look at priority scheduling, all the other algorithms that we have discussed so far, that is first come first serve or the shortest job first, they are, you may say that they are a somewhat variation of priority scheduling. For example, in the case of shortest job first, priority is given to a process having the least burst time requirement, or first come first serve. If all of the processes are present in the system, the arrival time will be given priority over all the other characteristics associated with a process. So priority scheduling can be considered as a parent class of all the other scheduling algorithms. So you can see that in priority scheduling, we have a number associated with all the processes, and a process having the highest priority, it can be taken by the scheduler and being placed into the processor. Just like as we had the problem with the shortest job first, over here we also have a downside, and the downside is somewhat similar compared to the shortest job first algorithm. And the problem is starvation, that it is possible that a process having a low priority, it may have to wait for so long by and it being bypassed by other processes having higher priority, and this particular process with a lower priority, it may has to wait indefinitely for the execution. So starvation is again a problem with priority scheduling. However, we can solve this by a technique that we termed as aging. That when with the passage of time, we can increase the priority of a process. So in this way, if a process enters into the system having a priority of 99, after some time its priority will be increased to 98, then to 97. So after a while, after some time, its priority will be higher than all the other processes that are present in the system. So it will get executed. So in priority scheduling, we can solve the problem of starvation through a process or a technique of aging. So as time progresses, we can increase the priority of a process. So just to make sure that eventually this process will get executed. So over here we have an example of priority scheduling. This time we have 5 processes having different burst times. However, in this scenario, we are more interested in their priorities. P1 has a priority of 3, P2 has a priority of 1, P3 has a priority of 4, P4 has a priority of 5, and P5 has a priority of 2. So you can see that these priorities are associated with the processes, and the scheduler can select a process just based on the priorities. To make things simple, we are assuming that all of these processes, they arrived at the system at time interval 0. So to understand this example, you do not require to understand the arrival time, and you just have to consider the priority, and the process having the highest priority, you can just pass it on to the processor. So as you can see in this example, P2 has the highest priority, then we have P5, then we have P1, then we have P3, and at the end we have P4. So these are the processes and their order of priority. And here we have the Gantt chart. As you can see that P2 having the highest priority will go into the system first, and as this is a non-primitive type of algorithm, so P2 will remain in the processor unless it completes its execution. So once it completes its execution, the scheduler will again look into the ready queue and look at the priorities of the processes that are present in the ready queue. So among the processes that are present at that time, process P5 has the highest priority, so it will be selected and given to the processor. And then once it completes its execution, then the highest priority is associated with P1, and then we have P3, and then we have P4. And this is how you will develop the Gantt chart for this particular problem. So now you can see that as all of these processes arrived at time interval 0, so it will be quite straightforward to compute the waiting time for each of the processes. So over here we have the average waiting time for this particular scenario, that is 8.2 seconds. I skipped a step deliberately, so you should be able to compute the waiting times for each of these processes on your own and just verify that the average waiting time for the whole scenario is 8.2 seconds. All right, students, so that is all for today. Today we discussed shortest job first and priority scheduling. Both of them are a type of non-primitive CPU scheduling algorithm. In the previous session, we discussed first come, first serve scheduling algorithm. In the coming lectures, we will discuss the primitive class starting from round robin, followed by the shortest remaining time first and the priority scheduling. And we will try to wrap up the whole discussion by having a deterministic evaluation where we have different algorithms applied on a single scenario. All right, students, please stay safe. Thank you.